Great, great. Problem. Thanks for taking the trouble. Okay. So now we'll briefly be talking about the failure modes, and then we'll move into what happens when you have more than one cache and what happens when you have more than one CPU. Because as you can think, there are a lot of problems that might happen, right? So in any kind of hardware system, there is a measure known as dependability. Can you all see my screen?
Yes, we have.
Okay, okay. So if okay, fine. There's a measure known as dependability, which means how reliable the system is, and then there's the interruption, which is the interruption from the service. And top tier services are supposed to be very reliable. For example, Amazon claims uh, the three nines. So by three nines, you mean that 99.999% uptime for all of its data, right? So uh, you want a high level of reliability in your hardware. So you can develop a bunch of metrics, but those metrics may or may not mean anything. So one metric that hard drives and SSDs use is something known as MTTF, which is mean time to failure, which, as the name suggests, tells how long before the drive fails. And there's also an MTTR, which means mean time to repair. So the mean time between failures is the sum of these both. So the thing is, it's a very misleading number, okay? Because if you see the MTTF of modern hard drives, it's something like 1 million hours, right? And 1 million hours is like several years, like it's like 5, 10 years worth of service, 100, even like there are drives that claim an MTTF of like 10 years, 15 years, 20 years, yet the thing is, in Google's data centers, there are probably hundreds and thousands of drives that fail every day because what the MTTF tells you is the average time that a drive takes to fail. There are drives that can fail very fast for any number of reasons, right? If the temperature conditions are less than ideal, if there are vibrations, if there is a manufacturing defect or something. So at the scale of a large data center, which is what you call warehouse scale computing, you have to assume that some hardware will fail every day, and you have to build in your systems in a way that the data is saved. So over here you get into concepts such as RAID. Okay, so a RAID is a redundant array of inexpensive disks, which is like an array of hard disks, and you go into details like the parity of hard drives. So basically, parity over here is the concept that you can have a property known as a checksum, which is that all the bits in a string should add up to a certain number. And if they don't add up to that number, then there is one bit that is probably wrong. So just by storing parity bits in another drive, you can reconstruct lost data. So you can read more about RAID configurations online. There's RAID 0, which is just connecting two drives together. And then there is RAID 1, which is mirroring, where you mirror one drive to the other hard drive, right? And then there is RAID 2, which is striping, which is like you store half the data in the first drive and half the data in the second drive and you interleave it. Then there is interleaving plus parity, RAID 5, RAID 10. There are various configurations. And all of them do some very interesting things to back up data and to ensure that you can recover the data if any one of the drives fail. So in this you come in, there are concepts such as the Hamming SEC code. The Hamming distance is the number of bits that is different between two bit patterns. So minimum distance is 2. So if the Hamming distance is 2, it gives you single bit error detection, which is like parity codes. So basically, you create an algorithm that detects single bit level errors, and as long as there is only a single bit error, you can detect it. Basically, if the number of bits are supposed to be even, You can detect which bit is flipped and you can correct it. This is also the concept behind ECC memory, by the way. You might have heard of systems having ECC memory. So at industrial grade systems in servers and all, instead of SODIMMs like SO DIMMs, like dual inline memory modules that your laptops or your PCs have, you have ranked DIMMs, RDIMMs, which support ECC memory. So ECC memory has error correction code built in to the memory. This can come at the expense of a little bit of nanosecond or millisecond level of latency, but the point is that at the level at which data centers operate, random cosmic errors like solar flares from the sun or supernova explosions or even radiation from under the ground can affect the integrity of data. And there's a very famous story about Google, like how Jeff Dean and Sanjay Gehmawat, right? Bit error. Google. There's one famous story. In 2001, basically, Jeff Dean and Sanjay Gehmawat identified that random bit errors caused by faulty cheap memory in Google's rapidly scaling servers were causing search index corruptions. So by auditing the raw binary data, they realized that the problem was physical, not logical, prompting a complete rewrite of the system to manage this failure. Okay. So they were searching for days. They were like reading through the entire code. They were like going into the compiler, they were going into the kernel, and they figured out that basically when you have thousands of hard drives and petabytes of memory, uh, just having the memory in a data center can cause bit corruptions like random. The thing is, at the level at which semiconductor chips operate, you have to realize that these chips are incredibly small. um, if I had to ask you a simple question, like what is the color of a transistor, of a modern day transistor? Like, can anyone answer that? Like, the chips that make up CPUs are called transistors, right? So, what is the color of a transistor? Anyone?
आई मीन क्या तो शायद वायर जैसा होता है छोटा सा।
So, so the correct answer is that transistors have no color because transistors are smaller than the property of color. Basically, the thing that gives things color is light, right? So you might have studied in 12th standard physics that light of 600 nanometers to 800 nanometers or 500 nanometers to 800 nanometers is your Vibgyor spectrum, right? So visible light wavelength. So if you see visible light wavelength, so promise all of this is relevant. It will seem like what unrelated stuff am I talking about, but you'll figure it out. So basically, it's around 600 nanometers to 700 nanometers. Now, the size of a modern day transistor in a modern day chip is less than 50 nanometers. The transistors are, what this means, that with an optical microscope of any magnification, you cannot see a transistor of a CPU. You can see bacteria through an optical microscope, but you can't see a transistor. The transistors are smaller than bacteria, they're smaller than viruses. They're so small that they cannot be seen with any known magnification. They can only be seen with electron microscopes because they're so small. So the problem is at these levels, quantum physics begins to take over. Electron tunneling happens, like randomly electrons appear on the other side of the chip, and you cannot explain why. It's just uncertainty principle at action, right? So these kind of random bit errors happen, and your system also has random bit errors that happen all of the time. The only thing is that we cannot stop these errors from happening. Instead, what we have to do is we have to assume that these errors happen and we have to take measures to fix them. So there are like sec dead codes. There you can like go read a lot about this, but it's very interesting stuff. What computers do to deal with random bit errors, and this is a physical problem. There's nothing you can do in hardware to fix this. You can only deal with it in software. All right. So now we come to virtual machines, and we come to this because virtualization is a very important feature of operating system design and computer organization. So your host computer emulates a guest operating system and machine resources. So it isolates multiple systems from each other. You can have multiple VMs running on the same device. It avoids security and reliability problems, and it helps in sharing resources. So the thing is, one of the earliest implementations of VMs was the IBM VM 370 in 1970s. You'll be surprised to know that the in 1970s we had better support for VMs than Microsoft Windows did till about 2015, because Windows was never designed keeping virtualization in mind, so they had to kind of reverse engineer it in, right? So there is a system known as a virtual machine monitor, which is like a super user. In Windows, this is also known as the hypervisor. So it maps virtual resources to physical resources. So if you log into AWS and you see vCPUs, right, for virtual CPUs, so the hypervisor is what controls all of these resources. It controls memory, IO devices, CPUs. So you can have like maybe 64 cores on a physical system, but you can map them to like eight units of eight vCPUs. So the guest code runs on the native machine in user mode. It traps to the virtual machine monitor and privileged instructions and access to protected resources. So basically, when your operating system needs to do anything that requires kernel level access, which is like reading to memory, writing to memory, so that is all kernel level operations, right? Reading and I mean not reading, writing to memory mainly. So all of the interrupts are handled by the VMM, which gives you access to the actual hardware at the end. And the guest OS might be different from the host OS, and the VMM handles real IO. Like you emulate a generic IO device, but ultimately you have to give access to the real IO, right? So one example of this is timer virtualization. So in a native machine on timer interrupt, the OS suspends the correct current process. It handles interrupts, selects and resumes next processes. With virtual machine monitor, you suspend the current VM, handle the interrupt, select it and resume the next VM. So if a VM requires timer interrupt, it emulates a virtual timer. So the thing is, support for virtual monitoring and all, believe it or not, it has to come from the instruction set. Yes, you can do it in completely in software, but the problem is that unless your hardware natively supports this, it is very, very hard to do. And if your OS is not built to support it and your hardware is not built to support it, then no amount of hacking will make it fix. I'll give you a case in point. Do you guys know that ARM chips can now run x86 Windows, like the normal Windows operating system? Like a Raspberry Pi can actually run Windows, the same Windows that your laptop runs.
Bhaiya, but even though x86, I mean, x86 also compiles to RISC-V, right? I mean, first the
Risk based instructions, but
yeah.
that's not the same as compiling to ARM. So, in the entire history of software development and hardware development, there is only one company that has managed to switch architectures twice successfully without causing massive pain for users. I think we all know which that company is. Any guesses? Which company changed their
Apple.
hardware instruction set architecture without changing the user experience at the end? Any guesses?
Apple भैया.
Apple, yes. So, which two times did they do it? Do you know?
From PowerPC to x86 and from x86 to ARM.
Correct. So, Apple did it twice. And yeah, they're the only people that have done it twice. They're the only people who even done it once properly. So, MacBooks originally ran PowerPC. PPC, it's still a backend for LLVM and other compilers. So PowerPC was the backend, and they switched to x86 by providing a software known as Rosetta. So the Rosetta is named after something known as the Rosetta Stone. Okay, so the Rosetta Stone was one of the biggest archaeological findings where which had like one single announcement written in three languages: Egyptian hieroglyphics, Demotic, and ancient Greek. So this was very important because at that point we knew that hieroglyphics are a language, but we had no idea what that language meant. But luckily, archaeologists did know ancient Greek. So they were able to map the hieroglyphics with the ancient Greek, and that enabled cracking the language. So in this case, basically Rosetta sort of transforms the PowerPC instructions into x86 instructions. And now recently they did it again while moving from x86 to their ARM architecture with Rosetta 2. And they were very successful because most users had very little problems. The only thing that took time was adding Windows support for Mac. I don't know if it has still arrived or not. Last I checked, it was Parallels for Windows was still not working very well. There were a few GPU applications on their Metal GPU driver that didn't work well, and I think Linux took a few years to work, mainly because Apple wasn't cooperating. But now they have Asahi Linux that works. So the comparison, this is this thing, your Qualcomm and Snapdragon. So Qualcomm has been trying to sell chips that run Windows for years, like Snapdragon based laptops that run Windows, ARM based laptops. So the idea here is that ARM is inherently a more energy efficient architecture than x86. So the promise is that if we can use a mobile chip to run a desktop operating system, we can get like 15-20 hour battery life on laptops in theory. But how it plans out is Windows runs so poorly on this thing on Snapdragon that they've been developing this for 5-6 years. There's still not one commercially available laptop or tablet that runs Windows well on Snapdragon chips. So this is because in this case, I think the problem is more with Windows than with uh, Qualcomm's architecture. But the only reason that Apple pulled this off is because Apple owns its operating system and its instruction set architecture. So you can imagine like how important the both need to be coupled, right? So that's this is why like emulating different systems on different OSs and different systems is so hard. Like yes, you can run Docker containers, but you can't run like Linux based Docker containers on Windows directly unless you are running something like WSL. You can run different Linux distributions inside Linux, but you can't run Linux-based Docker containers on Windows directly unless you run it inside WSL. And even WSL is something that Microsoft had to engineer. So both of these things for virtualization, they have to be built in into the instruction set architecture, into the operating system, and you need support from both sides. Otherwise, it's very difficult to get it right. So basically, virtual memory is the concept that a user does not have to worry about how much memory their resources are using. Like when you declare like malloc or realloc or free or whatever, you allocate memory, you play with memory, or in something like Java, you declare objects of arbitrary large sizes, right? You never have to worry about how much memory is there in the system unless you are programming microcontrollers. If you're doing that, then you have to worry about the memory. But the main point is that operating systems today, they hide the fact that they have limited memory from you. So they do this using a concept known as virtual memory. So the main memory is a cache for the secondary disk storage, if you think about it in a way. Your cache memory stores some of the data of your RAM, right? And your RAM stores some of the data of your hard disk. So similarly, your register stores some of the values of your cache. Your cache stores some of the values of your main memory, and your main memory stores some of the data of your secondary disk. This is also why the memory hierarchy is a true hierarchy, right? Each level below has all of the data of the level above it. So this is managed jointly by the CPU hardware and the operating system. Programs share the main memory. So all the programs that are running, they have to run on the same RAM, like same 8 gigabytes or 16 gigabytes or 32 gigabytes of RAM that you have. Each gets a private virtual address space holding its frequently used code and data, protected from other programs. So I am giving you all an assignment, like in C, write a program to like get the process ID and get the print the memory address, and see if you can print the same memory address for different programs. It turns out that even if you make two C programs run together, provided you turn off something known as address space randomization, you can actually get multiple programs to have the same address, zero. Like you can make them have the same memory address, that when you print the memory address of the pointer, you'll get the same number, not zero, you'll get the same number. So that is because each process that is running in memory, we discuss processes, right? Processes have their own stack, they have a heap and all that. So each process has its own private memory that does not that maps to real memory, but it's not visible to the developer. So you, the developer, whenever you print a memory address, always remember this. It's a common interview question also, that whenever you print a memory address, like you print the memory address using a pointer, or you print the memory address of an object or using the dereference operator, it is always a virtual memory address. The CPU and the OS never lets you see the physical memory address, and there is no way to see it. The operating system does that virtualization. The only place where you can see real physical memory addresses are microcontrollers where there is no operating system. So just remember that. So you have virtual addresses, right? So how do you translate these to real addresses? You do something known as address translation. So one idea was that, how do you bring things in and out of memory, right? It's a question, right? That I have some data, I have to put the data into memory, I have to move the data out of memory, but what is the unit of data that I have to move? Does my CPU have to deal with individual blocks, individual bits, individual bytes, individual words? No. Instead, what we do is we create pages. So each page is something like 4 kilobytes by default. There are options like huge pages that you can enable within the OS. Linux allows you to set transparent huge pages, with where you can have one page that is like 1 gigabyte also. So these pages are fixed units of memory that your CPU deals with. So your CPU pulls data in and out in the concept of pages. So each page has a virtual page number and an offset, and this goes through a address translation mechanism through a chip known as the MMU, the memory mapped unit, and this is what translates physical addresses to virtual addresses. And always the address that you, the developer, see is the virtual address. You never see the physical address. So obviously, if the CPU is looking for a page, it's looking for some data, and that page is not available in the main memory, you have to segfault. There is no other choice. So on a page fault, the page has to be fetched from disk. This takes millions of clock cycles because again, the SSD or the hard disk is very, very slow compared to the processor, and it has to be handled by the operating system. So everything above this is handled by the hardware. Cache misses and cache hits are handled by the hardware directly, but this segmentation faults are handled by the operating system. So we want to minimize this page fault rate as much as possible. So one is that again you have to just your CPU needs to have visibility of how many pages you have, right? And where those pages are. So we create something known as a page table. So I know all of these concepts sound very softwarey, and hopefully somewhere in the middle of the year, if we ever get around to covering operating systems, it will be about all of these concepts because all of these is software. But just go over it briefly for now. So the page table stores the placement information. There's an array of page table entries which is indexed by the virtual page number. The page table register in the CPU points to a page table in physical memory. If the page is present in memory, then we get the data. If it is not present, then we swap in the page from the hard disk. So it's swapped in, and that's why your swap space is also important. It's a parameter that you can set while installing your operating system. So to reduce your page fault rate, you have to prefer LRU, which is you try to replace the oldest pages that are not used anymore. So disk writes take millions of cycles. So we try not to write to the disk constantly. We want to do in blocks. And you know, this block writing, you have to remember that block writes are much faster than individual writes. So if you have to transfer like 100,000 small files, like you have 1 lakh small files or 1 million very small files that you want to transfer from your PC to your hard disk or to your SSD, even more than compression, the thing that helps the most is tarring all of them together. So, do you all know what a tar is and how a tar is different from a zip? Can anyone tell me that? What is a tar? What is a tar file and how is it different from a zip?
R is uncompressed. We can compress it with the
Okay, tar is uncompressed, that is correct, but what is a tar? Surely you must have seen software like tar.gz and all, right? So, what is a tar file? Anyone?
I mean, yeah, it just bundled all the files without compressing.
Yes, correct. So a tar file basically joins the end of one file to the beginning of the next file. So if you have like say 10 text files, your tar file will combine them all into one large text file with one beginning and one end. So the advantage of tarring a file is that you can convert multiple hundreds of files into one large file. And when you do this, then your disk has to do one write instead of doing like 1 million separate writes. So it can store the entire block of information in one place instead of having to create one page table entry or one inode block for every single entry. So that's why a lot of software is both tarred and compressed. So first you tar the whole file to combine all of the multiple smaller files into one file, and then you compress that file. So that's the fastest way. That's why just compression is not enough, because compression can reduce the size of the files, but it can't reduce the number of files. Tarring is an operation that reduces the number of files. So that's why it's fast. So it's done using a software called GNU tar, and you can check it out. So the thing is here now we are coming to address translation, right? I mentioned that we have to translate addresses. So let's say you have 4 KB pages and you have 16 GB of memory, right? So how many pages would you have in memory then? 4 kilobytes. So let's do that calculation actually. I'll do it in Paint. I don't need a calculator. I just need to show you what to do. So 1 GB is 2 to the power. Okay, let's just reverse that and do that. So yeah, 1 GB is 2 to the power 30 bits. Okay, 2 power 30 into 16 is 2 power 4. Right, right. This is 16 GB of memory, and each page is 2 power 12, because 1 KB is 2 power 10, so 2 power 12. So if you equal it here, you will get 2 power 34 divided by 2 power 12. 34 divided by 2 power 12. So how much is this? So 2
2
power
power
12,
22 by.
2 power 22. How much is 2 power 22 roughly? Can you tell me?
Mm,
So 2 power 20 is 1 megabyte. 2 power 22 will be 4 megabytes, right? Right.
yes, yeah.
But yes.
Now, uh, do you see the problem with this? This is one file, right? I mean, one program's page table. Now, assume that you have like 100 programs running, right? And you have 4 megabytes, meaning your table will have 2 power 22 entries, which is a very big number, man. It's a huge number. It is like 1024 into 1024 into 1024. So if I take the calculator, uh, and we do like 1024 into 1024 into 4. So tell me, is searching such a big table ever going to be fast? This is the table for one process, and the table has these many rows. Do you think searching a table, such a big table, is ever going to be fast?
Nope.
Right? It's very big. So you have to come up with a way to make it efficient. So again, you use the same concept of caching. Like, you created a cache for main memory, right? So you create a cache for the page table. So the cache for the page table is something called the translation look-aside buffer, TLB. It's a bad name because translation look-aside buffer does not tell you anything about what it does, but please remember that name. So the TLB is basically a cache for your page table. It stores the most important address translations that are there. So basically, only the parts of the page table that are accessed the most frequently are stored in the TLB, so that you don't have to fetch so much of information. You don't have to search such a big table for every single entry. So address translation would require a lot of memory references. So access to page tables luckily has good locality. So using a fast cache of page table entries within the CPU is a good move. It's something called the translation look-aside buffer. So this has 16 to 20, 512 page table entries. So this has 0.5 to 1 cycle for hit, 10 to 100 cycles for miss, and 0.01 to 1% miss rate. So you can imagine 99% of the time the data is there in the TLB, and the TLB is 10 times faster than the page table. So you have to wonder, like, how does the TLB pick the right page tables, right? From this large list to fit. And yeah, there's a lot of magic that goes on there. So yeah, so the TLB just stores the most important page table entries. So if a page is in memory, load the page table entry from the memory and retry. It can be handled in hardware. It can get stuck for more complicated page tables. In software, raise an exception with a fault handler. If the page is not in memory, you have a page fault. So the OS handles the fetching the page and updating the page table, then restart the instruction which was faulting. So TLB mishandler, TLB miss indicates that the page is present, but page table entry is not in TLB, which is the good one. Like, okay, fine, it's there in the page table, but it's just not there in the TLB. That's okay. But if the page is not present, then what again you segfault, because that means that that location that you need is not there in memory, right? So that's why you segfault when you do, you can segfault when you do like a out of bounds access or something, because something might not be there in that location at the location that you're trying to handle. So the page fault handler uses virtual faulting addresses to find PTE. It locates the page on disk, chooses a page to replace if the page is dirty. If dirty, write to disk first. So that, because again your TLB also needs to maintain consistency, right? So read the page table into memory and update the page table, make the process runnable again. So TLB and cache also interact. If the cache tag uses physical address, then you have to translate it. So basically, your cache stores data, right? So that data can also include addresses. So there are two ways that your cache can store addresses. One is a virtually mapped cache, where the cache also has virtual addresses only. So in that case, you have no problem, because you don't need the TLB only. It's all virtual address. But if your cache stores physical addresses, then that when CPU requests for data and you find the physical address, you have to translate it before giving it to the CPU. So there are physically tagged caches, virtually tagged caches. There are hybrid approaches. It all depends on what kind of CPU you're designing and what you're designing for. So one important concept that comes into all of this memory management is protecting the memory. Okay, so different tasks can share parts of their virtual address spaces, but they need to protect against errant addresses. They require OS assistance. So hardware supports OS protection. Like basically, hardware gives you a few simple instructions that give you like safety. Like they store the kernel needs some special instructions. Like basically, let's say that you can only write to a memory location. Only one person can write to a memory location at once. But how do you stop software from, how can you prevent writing code that will like try to write to the same memory address at the same point from two different processes? This is where hardware design comes in. You can give special instructions. Like there are instructions like fused multiply add that do a multiplication and addition in the same instruction. There are set and lock instructions which allow you to uh, uh, like set a value and not change that instruction until the lock is handed over to another process. So there is a kernel mode and there are privileged instructions that only the kernel can execute. So there are some CPU instructions, ISA instructions that only the kernel can execute inside ring 0 or ring 1, which is the most privileged instructions. And uh, only the kernel can interact, and the user has to interact with the kernel through the API. So just like all of the software web development and all that you do has APIs, the kernel also has an API, and that API is called a system call. Okay, so basically the kernel provides a set of APIs, and that API is used to write all of your programs. If you see malloc in C, right? Does anyone know how malloc is implemented in C? Okay, do you know what malloc does at least? That you should know. Anyone?
Allocates the memory and returns a void pointer.
Correct. So malloc allocates the memory and returns a void pointer. So malloc is implemented using something known as the SBreak system call SBRK. Okay. So let's see. Uh, let's see. SBR, SBreak, and so basically, that's great that Stack Overflow is the correct biggest link that rarely happens these days. So basically, malloc calls the number of SBRK and BRK instructions, and and there's also it's basically malloc itself is not a system call. It's a C library function that manages the memory using SBreak. So similarly, printf implementation using syscall. So if you are ever going for a kernel interview or even a compiler interview, you might see something uh, asking to implement printf, and this is a question that messes up many people because you start learning C programming with printf, right? So how the hell do you implement something like printf? So printf you can implement it like this using something known as the write system call. So the write system call has parameters like std out message and the strlen message. So this is a very simple
हेलो आशुतोष भैया।
अच्छा, सिर्फ मेरा नहीं रुका है मतलब।
हाँ,
अच्छा।
मैं भी डाल गया था एक रुको मैं
Can you hear me?
कॉल कर।
हाँ भैया, अभी
हाँ भैया, बीच में फ्रीज हो गए थे।
अभी आ रहा है भैया।
आ रहा है?
हाँ भैया आ रहा है अभी। क्या है?
चलो। हाँ, तो वही मैं बोल रहा था कि बेसिकली system calls have a lot of power. Okay, like sbreak system call or mmap system call, these allow you to arbitrarily allocate memory in like different places. So if you don't use them correctly, you can fuck up your OS, you can fuck up your program, you can freeze your entire system, and you can take it to an unrecoverable state. This is why writing libraries is very hard, and people use the libraries that other people have written. So system calls have a lot of power, and system calls are the API that the kernel provides. Okay, so uh, I hope everyone understood that concept. Okay, so Yasha asked, can't we just initially give a low size page table and then on demand we expand via page fault? So usually the thing is your one good concept is that you usually want the page table size to stay constant, because then your CPU and your program can make assumptions. Like let's say that you want to pull half GB of data of a game that you are running to play the next level, right? Like let's say earlier games, if you had this GTA Vice City, anyone played GTA Vice City? If you go to the island, there used to be a loading screen. Does anyone remember that? Like
yes.
you go from
And
one island to the other island, there used to be a loading screen. Do you know why that loading screen was there?
no, भैया।
Basically, it was there because to give time to the operating system to load that part of the game into memory. Okay. So systems had very limited RAM when GTA Vice City came out, right? I think even back then GTA Vice City was like half GB or 1 GB in size, and there were systems that had only 512 MB of RAM or like 256 MB of RAM, especially the PlayStation and all at that time. PS1 released with like 256 MB of RAM. So basically, you have to load the game in parts, right? You have to load the first part, and then when you go to the different island which has different textures and settings, you have to load the next part. That time, dynamic loading and all, lazy loading and all wasn't invented. So you have to load the game in parts. Now, how do you know how much to load, right? It's a big problem. If your page table size is variable across programs, I mean, not across programs, within a program, if page table size is variable, then your OS will never know how much data to pull in, right? You can't do calculations on that. You can't do pointer arithmetic. You can't know where to go. So that's why page size is constant. Yes, you can vary the page size. As I said, there is a parameter in the OS that lets you vary the page size. Transparent huge pages and page size, you can vary the page size as much as you want, but you can change it to one value and then the OS will apply that value for that process. You can't vary it within a program because using that would just make design a lot harder. Okay. So the memory hierarchy, basically the big picture is that common principles apply at all levels of the memory hierarchy based on the notions of caching. At each level in the hierarchy, there's block placement, finding a block, replace, write policy. So block placement is where to put the data. So that's determined by associativity as we discussed for cache. Direct map caches have only one place where you can replace the block. N-way set associative is you have n choices within a set. If you have two sets, if your set has an associativity of two, then in each set you can put two pieces of data, and then fully associative is anywhere. Higher associativity reduces the miss rate, but it increases the complexity, cost, and access time. So hardware caches reduces comparison to reduce cost, and the virtual memory has a full lookup table. So where to replace blocks, you can either use LRU, you can use random, you can use 1 bit replacement, 2 bit replacement. You can have different write policies, like whether you want to write through. So basically, if some data is updated in the cache, it has to also be updated in the main memory, right? So either you can update both of them at once, or you can just keep store the dirty bits in the cache, and when the cache is cleared for the next process, at that time you can write it back to the RAM. This is write back. This is much more efficient because you're combining 4 5 writes into one, and for virtual memory only write back is feasible because disk write latency is very high. So write back is implemented more than write through. So misses come from various things. This compulsory miss, which is the cold start miss. Basically, the first time you load a program into memory, your cache will have no idea which data is accessed more frequently, which data is not accessed more frequently, because the program is running for the first time, right? So the first time you run any program, it's going to be the slowest because you have compulsory misses. Then you have capacity misses. This is due to the finite cache size. So this can be that you can write a program that is bigger than the cache, and it's so much big that the cache always misses. So this is also a thing you can try. You can write a C program that accesses data in such a way that the cache always misses, and you can get horrible performance. Then you try to write a program in which the cache does not miss, and you'll get much better performance. So then there are conflict misses, which is not due to capacity, but it's due to conflict in the data. Like the data itself has to be stored in one location only within the cache, and there it's the conflict. So you have many design parameters to think for. You can either increase the cache size, increase the associativity, increase the block size, but each of them comes with trade-offs. If you increase the cache size, uh, cost will increase. It will decrease the capacity miss, but it might increase the negative. It can negatively affect access time. If you increase associativity, you can decrease conflict misses, but it will increase access time. If you increase block size, it will decrease compulsory misses because more of the data is pulled into one block, but it will increase miss penalty. So for very large block size, it might increase miss rate due to pollution. So each of these approaches has trade-offs, right? So there are different cache characteristics. There are different ways to design caches, and usually we use finite state machines for designing caches. So does anyone know what a finite state machine is? You might have studied Mealy machine, Moore machine in automata theory, FLAT or ATFL, or I don't know what you guys call it. Anyone? Anyone knows what a finite state machine is? The concept of a finite state machine. Okay, so a finite state machine basically has a series of sequence control steps, and each of these result in an output. So basically, it uses combinational logic. For every single pair of inputs or any single combination of inputs, there is a fixed output. Okay, so I'll just take a sip of water for a minute. So brain check. Till then, if you have any questions, you can ask them. I'll answer them. Any questions so far? So any questions so far? No, right?
No,
Nobody?
yeah.
Okay. Okay. So now we come to the problems, and now we come to the biggest problem, cache coherence. Okay. So suppose you have two CPU cores that share a physical address space. At timestamp 0, memory is 0, CPU A has cache has nothing, CPU B's cache has nothing. In the first time step, CPU A reads X, okay, some data value, and A's value is now set to 0. Now CPU B reads X and the value is also 0. Now in third one, CPU A writes 1 to X, but CPU B's cache still has the value 0. And the memory also has the value 0. So can someone explain the problem here to me? What is the problem here? Anyone? Just explain this table. Like what is going on here? There are two CPUs. Two CPUs have their own caches. Okay. CPU A is reading the value of X, and then CPU B is also reading the value of X. CPU A writes the value of X. It does some computation and it changes the value of that X to 1. And then through write back or write through or whatever, your main memory has a value of 1. Okay. But CPU B is still running that process, and there the value is still 0. How do you
This is
avoid
a
this?
this is a race condition.
I mean, I don't know if I would call it a race condition. It's an inconsistency. Means, how can you avoid this? Tell me that when you have
Mm,
four cores or eight
by
cores and all of them have their
by
own cache, how
using
do you avoid
semaphores or something, maybe.
in hardware?
uh Hardware, I don't know, but we can I mean, we can use semaphores or something like something to like keep the process waiting until one operation finishes or something like that.
So I'm again once again asking the audience, did everyone understand the
Uh,
problem at least?
yeah,
Yeah,
we should have the shared cache and the option to flush to the shared cache.
yeah, yeah,
Correct.
exactly. So, yeah. So there's only a few things that are possible. Either that all of the caches have to talk to each other and agree on a value, or you should have some way for it to communicate, or you have to have a thing where if one value is updated in one cache, then the value should be cancelled out in all of the other caches. Like it should be marked as invalid. The memory, the CPU should force a reset. So there are a lot of protocols for this MESI protocol, MOESI protocol, MOSI protocol, whatever. So there are a lot of solutions to this, and this is the basically what all multi-core processing is about. It's about avoiding this cache coherence problem. So we'll go into it in a detail. If you all are willing to listen for maybe like 20-25 minutes more, we can do it today or we can do it on another day if you're already tired. So I leave that
No,
to
yeah,
you
you
guys.
can
Oh,
you can continue
yeah.
here.
Okay. So the coherence problem is basically that you have to read the most recently written value. So P writes X, P read X. So P1 writes X, P2 reads X. Now P1 writes X and P2 writes X. All processors see the writes in the same order, and you end up with the same value. So there are many protocols for this. So operations performed by caches and multiprocessors to ensure coherence. One is that migration of data to local caches which reduces bandwidth for shared memory, replication of read shared data, which reduces contentions for access. You can have snooping protocols where each cache monitors the bus for reads and writes. So you have a data bus, like a cache bus that has all of the information about the reads and writes that are coming in, and every cache listens to the other caches. Or your directory based cache protocols where cache and memory record, they share their status on in a block. So there is invalidating snooping protocols exist where cache gets exclusive access to a block when it is to be written, with broadcasts it to invalidate a message on the bus, and it reads in another cache miss. So basically, CPU first you have 0 in the memory. CPU A reads X, cache miss for X. CPU B reads X, which is also cache miss for X. CPU A writes 1 to X, which invalidates the value in B. It's cancelled out. Then CPU B, when it reads X in the next cycle, then it's 1. So you wasted one clock cycle, but at least you ensured consistency. So we'll read about more policies soon. So when the writes are seen by other processors, so seen means like a read returns the written value and it can't be used instantaneously. So there's an assumption here that a write completes only when all the processors have seen it. A processor does not reorder writes with other accesses. So P writes to X and then writes Y. So all processors that see the new Y also see the new X. Processors can reorder the reads, but not the writes. You can read in any order, right? That's fine. But the moment you're writing something, then that writing order becomes important. Because if A writes a value first and then B writes a value later, then B might have written that value based on the value that A returned, right? So that A's write has to happen before B's write. It can't happen on the other way around. So there are multi-level on-chip caches. So here's an example of two of them. One example taken from the Raspberry Pi and many modern smartphones called the ARM Cortex A8 and Intel Nehalem, which is I think the Atom series. It's a very small processor. So in Cortex A8 we have split instruction and data caches. In Nehalem, we have split instruction and data caches also. L1 cache size is 32 kilobytes for both of them. Associativity in A8 is four-way D set associative, and in Nehalem it's eight-way set associative. In Intel's processor, we use approximated LRU, but in A8 we use random. L1 block size is 64 bytes in both. write policies, write back, write allocate. So you can see here then there's L2 cache. In A8 there is no L3 cache, but NALM does have an L3 cache. So we have had even processors with L4 caches before. It famously came in I don't know one which generation of Intel processors had EDRAM, I think it was called. Uh, Let me Google that also for you. So Intel EDRAM uh, L4 cache. Which processor had that? Yeah, yeah. It was used in fifth gen Broadwell desktop processors. It had 128 MB of on package cache, which was like it acted as a buffer between the L3 cache and RAM, and it was really good. But unfortunately, it was a little bit expensive because it was literally expensive. It was a very good. It helped with the performance a lot. Power consumption was high. That's why they stopped using it. And apparently they're trying it again in Meteor Lake. So yeah, caching always helps. It's one of the most oldest tricks in the book to increase performance. So TLB design also varies up across this. So the virtual address space is A8 is 32 bits. So 32 bits means 2 power 32, which means 4 GB. Whereas in i7 it is 48 bits. So 48 bits would mean roughly uh, it's a lot more, right? So if 30 bits is 1 GB, then 40 is 1 TB, and 1 TB into 2 power 8 is 256. No, yeah, 2 power 8 is 256, correct. So 256 terabytes is the theoretical address space for i7, which is a very big number. We're never going to have anywhere near 256 terabytes of storage on a single desktop processor, at least. It's a lot of data. The physical address space is 32 bits again, whereas for i7, some bits are reserved for other things. Page size is variable in A8. You can put 4, 16, 64 kilobyte, 1 megabyte, 16 megabyte pages, whereas here it's 4 kilobyte, 24 megabyte pages, and the TLB organization is also different. So both of these processes support something known as multiple issue, which has multi-bank cache cycles that allow multiple accesses per cycle, assuming no conflicts. Core i7 has some cache optimizations like return requested word first. It has a non-blocking cache. So non-blocking cache is like a cache that allows you to like access data directly without having it hits under a miss, and it miss under a miss also is allowed. So and it allows you to do data free prefetching. So again we come back to our favorite DGEM, double general exponent matrix multiplication. Obviously entire books will be dedicated to DGEM because DGEM is the most important single most important maths that we're doing today, right? It's all about all machine learning is all about multiplying matrices. So again there are mistakes that people make here. One is byte versus word addressing. So 32 byte direct mapped cache is there, but you don't consider byte 36 will map to block 1 because there are 4 byte blocks, and word 36 will map to block 4. So people make these calculation mistakes. They ignore memory system effects while writing or generating code. Iterating versus rows versus columns of arrays. Large strides result in poor localities. So basically, if your loops have a very large stride length, like they jump like 8 numbers at a time, 16 numbers at a time. So the speed that you gain from array access being contiguous is lost because you're like jumping so many numbers forward. So multiprocessor systems with shared L2 or L3 cache, there's less associativity that cores that results in conflict misses. More cores means you have to increase associativity. So you have to use average mean access time to evaluate performance of out of order processors, because out of order processors can execute instructions in an order that's different from like the instruction that they order that they were issued in. So you have to use more advanced metrics to measure their performance. So Intel. So then again, there's some pitfalls. So basically, to conclude, we'll take a look at a couple of common this thing. Like let's see here, cache coherence chapter over here. This is Professor Udareddy Bondugula's slides. So let me see if I can show you the cache coherence. Yeah. So let's uh, make this a little bigger so that it's easier for you all to read. I think already the slide text is very big, so it should not be that hard to read. So basically, you have different caches. So here you have two cores, C0, two sockets, basically two physical CPU sockets. So there are two CPUs on the system. Each of them have four cores. Each of them has four L1 caches, and each of them has four L2 caches. Each of the cores, and both of the CPUs share an like each of the CPU has one L3 cache, and that there are basically fabrics like Infinity Fabric that AMD has and Intel also has, which allows the two CPUs to talk together. So caches play a key role in all of these cases. They reduce the average data access time, they reduce bandwidth. So private processor caches create a problem. There are copies of a variable that can be present in multiple caches. We saw this. A write by processor P1 may not be visible to P2. P2 will keep accessing stale value from its cache, and this will lead to all sorts of cache coherence problems, right? So read is fine. Read write is a problem if when you after the write if you do a read. So processors see different values for you after event 3 with write back caches. The value written back to memory depends on which cache flushes or writes the value back. So this creates a very big data consistency problem, cache coherence problem, and yeah, even your compiler has to be aware about this. So processors shouldn't read stale data. Reading the address should return the last value written to that address. I mean, that's the logical thing, right? You need the latest data at all times, not some old value. So the solution is you use cache coherence. You can use either an invalidation based or update based protocol, Snoopy versus directory, or you can use compiler assisted cache coherence. So you have Snoopy bus protocol, you have an assumption that a shared bus interconnect where all of the cache controllers monitor all the bus activity, talk to each other. This is something known as snooping. So there is only one operation through bus at a time. The cache controllers can be built to take corrective action and like enforce coherence in this. It could involve updating or invalidating. So Snoopy, like this red line here represents the bus, and the moment like one value is written here, this the value in P2 is invalidated, and when P3 reads it, uh, it's it's used. So there's a basic question here, right? Is a block written by one processor later read by another processor before it is overwritten? So invalidate is like readers will take a miss. Basically, even though that processor has a value, it has an old value, the processor will tell the CPU, I mean the CPU will be told by the cache that that value is not present because the value is not the latest one. So you wait a cycle, and when the data updates, then there's a cache miss, then there's a cache hit after the value is updated. So there are because there's no use of doing one. One protocol is the MSI invalidation protocol, where I is the invalid state, S is the shared state, one or more cache copies, and M is the modified or dirty state, which is the only copy. It's encoded in 2 bits and updated by protocols like PR read and PR write. And there are bus transactions. So there's a state transition diagram for this. Again, yeah, let me. Yeah, it's not a very good diagram. Never mind. There's a four-state protocol also called Macy, which is a problem with them. Like reading and modifying the data is two bus transactions. Basically, first you have to read from the bus, and then you have to update the bus. But the problem is if the other processor is not using that data, then also you have to stop and flush the cache and update the value, right? The other processor will get slowed down because the cache is getting flushed, even if the data is not being read. So this adds an exclusive state which writes locally without a transaction. Memory is up to date, so cache is not necessarily owner. So there are now four states: invalid state, exclusive state or exclusive clean state. Only this cache has a copy, but it's not modified, so it's okay. There's a shared state where two or more caches can have copies, and there's a modified state where it's dirty. So again, this is the state transition diagram. You'll have to go study this in more detail yourself, unfortunately, because covering each of these will require like one whole lecture for each thing, and we don't have that kind of time. But there are scalability issues with Snoopy protocols. So Snoopy cache is ideally suited for bus-based input. Shared bus input saturates performance for large number of processors. So, I mean, the thing is your bus has data coming in and out. What if you have 256 cores, 512 cores, 1000 cores? That bus will get saturated, right? There will be thousands of values flowing in and out. So for 8 processors, beyond that, Snoopy bus protocol can't work because there's too much data to be carried around. So for non-bus based input, coherence messages can be broadcast. So one way is like you share it to all of the other cores at once. That is very expensive. Only a few processors can have data. So like there is a lot of problems that come in here. Basically, when you have a shit ton of memory to address, even where your RAM is on the motherboard matters. Like in Numa and Uma, the concept is like you don't have uniform memory access in Numa. So the RAM sticks that are closer to your CPU are accessed faster than the RAM that is the farthest away from the CPU on the motherboard. So we also have directory based approaches where memory or cache maintains a list or a directory of processes that have a copy of a block. On a write, memory controller sends an invalidate or update signal only to processes that have a copy. Memory also knows the current owner in case of dirty blocks, and the memory container requests for an updated copy. So this is like a generic solution sort of for solving this problem. So uh, now I think that concludes it for today's talk. Uh, Probably after Zenith and all, we'll go more into multi-processor design, multiple cores, and